So our last problem in chapter 19 actually is a really neat application of looking at Q versus K comparisons. And what it really does is it allows us to examine the separation of ions by what we call selective precipitation. So I want to draw a picture first for this to kind of hopefully help solidify this. We've got a solution that contains 0.2 molar magnesium chloride and 0.1 molar copper chloride. So these chloride salts happen to be all soluble. So what we're going to really have, and just draw a little picture here, we've got a little beaker here. It's got 0.2 molar magnesium chloride and 0.10 molar copper chloride. So what this really means, because these salts are soluble, is we've got magnesium ions in solution at 0.2 molar, and we've got copper ions in solution at 0.1 molar. We also happen to have twice as many chloride ions from magnesium chloride, so that's 0.4 molar, and twice as many chloride ions from copper chloride, and that's 0.2 molar. But because these guys are spectator ions, we're really not concerned about what they might participate and do in chemistry. So again, these are spectator. So the chemistry that we can see here is we're going to use hydroxide to separate these metal ions, which kind of tells us when we have hydroxide in solution, what we're really going to have when we add hydroxide is the formation of an insoluble precipitate of magnesium hydroxide or an insoluble precipitate of copper hydroxide. The KSP for these values is for magnesium hydroxide, it's 6.3 times 10 to the minus 10th, and for copper hydroxide, it's 2.2 times 10 to the minus 20th. So again, an important kind of qualitative skill to think about with KSP is the larger the KSP value is, again, larger any equilibrium value is, the more the equilibrium is going to lie on the right, which means for solubility, the more that we've dissociated or broken apart those ions. So when we have magnesium hydroxide in solution, we've got a larger KSP, which means more ions are allowed to be in solution as breaking apart from magnesium hydroxide, which means if we have a solution of magnesium and copper ions that we start dripping hydroxide into, we're going to reach the critical mass that's going to precipitate copper hydroxide first. So again, the question is what's the concentration of hydroxide that we need to selectively precipitate out the copper hydroxide and leave the magnesium having not reached yet its critical mass of hydroxide ions to facilitate precipitation. Okay, so again, an important point to note is we know copper hydroxide will precipitate first because it's the least soluble. And for this problem, we can see that there's actually 10 orders of magnitude. If you hear that word order of magnitude, 10 is an order of magnitude, 100 is 2 orders of magnitude. So this is 10 to the 10th difference between these two KSP values, which is a huge range of concentration that's different. So we should be able to selectively precipitate the copper hydroxide before we start getting to a hydroxide concentration that will start precipitating the magnesium. So again, we know the copper hydroxide is going to precipitate first. So a big question is, what concentration of hydroxide do we need for this to happen? So one way that we can think about this too, kind of an alternative question, is what concentration of hydroxide will we need to begin the precipitation of magnesium hydroxide? And as long as we stay below that, we know we will be above the concentration needed to precipitate the copper hydroxide, but again, still allow all of the magnesium ions to remain in solution. So I'm going to ask this question, and I'm going to solve it with some equations here. So the KSP then for kind of the magnesium concentration, 6.3 times 10 to the minus 10th is the value. It's going to be equal to the concentration of magnesium times the concentration of hydroxide. we actually know the concentration of magnesium that we have initially, and that's 0.2 molar. Okay? And so what we can do is we can put this in and solve for the hydroxide concentration that we need to have to begin to precipitate that magnesium hydroxide. So we can say that 6.3 times 10 to the minus 10th equals 0.2 times our hydroxide concentration squared. And so what we're really going to solve for is what hydroxide concentration would we need to be at to begin to precipitate this hydroxide, or I'm sorry, this metal hydroxide, magnesium hydroxide. So the concentration we need to be at if we solve for OH minus is 5.6 times 10 to the minus 5th molar. So again, what does this mean? The meaning of this, as long as the hydroxide concentration stays below this value, we won't precipitate magnesium hydroxide, but again, we'll be above that for what we need for our copper. So as long as the hydroxide concentration is less than 5.6 times 10 to the minus 5th molar, there will be no precipitate of the magnesium hydroxide. So let's find out the minimum hydroxide concentration, again, that we'd need for copper hydroxide to precipitate. We can treat this similarly. The KSP for the copper hydroxide is 2.2 times 10 to the minus 20th, and that's equal to the concentration of copper times the concentration of hydroxide squared. We know that the copper concentration initially is 0.1 molar. So going ahead and putting this into our same equation, 2.2 times 10 to the minus 20th equals 0.1 times our hydroxide concentration squared. And we get hydroxide concentration equal to 3.32 times 10 to the minus 10th molar. And again, meaning of this is the minimum hydroxide concentration to precipitate our copper hydroxide. All right, so as we drip, 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 drip in our hydroxide solution, as our hydroxide solution begins to approach 3.32 times 10 to the minus 2nd molar, we'll begin to precipitate our copper hydroxide. That copper hydroxide is going to be pulling that hydroxide out of solution, and that will continue to happen until we pull all of the copper hydroxide out of solution, and then when we continue to add hydroxide, it will continue to increase in concentration. So we'll increase in concentration, and as our concentration approaches the 5.6 times 10 to the minus 5th molar, then we'll begin to precipitate our magnesium hydroxide. So if we wanted, we could actually continue to do this so that we could precipitate both metal ions. Again, maybe filtering off the copper hydroxide first in order to separate. So kind of a really neat problem to get us to think about selective precipitation. Again, adding and dripping in hydroxide will selectively precipitate the less soluble salt first. And then as we continue to add in hydroxide, and we change the hydroxide concentration now, once we get to a critical mass for magnesium hydroxide, which is 5.6 times 10 to the minus 5th molar, we'll begin to precipitate that metal. So kind of a neat way to think about maybe like an acid-base titration, right? So this is a little bit like when we add in hydroxide, initially our hydroxide is going to find something to react with, right? So we're going to react with our copper and we're going to precipitate that out, which means we should see minimal changes in pH because the hydroxide that we're adding is being sort of soaked up by our copper. And that's going to happen until all of our copper ions are taken out of solution. And then our hydroxide is going to contribute to an increase in pH, an increase in the hydroxide concentration until we get close to 5.6 times 10 to the minus 5th molar. Once that happens, we will have reached the critical mass to allow us to precipitate the magnesium hydroxide. We'll continue again to precipitate the magnesium hydroxide not really changing pH until we get to a point where all of the magnesium has been used up. And then we'll at that point see another increase in pH. So kind of a neat way to, again, think about, if we were to kind of draw this here and think about a hydroxide concentration as a function of pH, we'd initially see an increase in pH until we got to a concentration that allowed us to start precipitating the copper ions. And then we kind of flatline a little bit because the hydroxide that would be added would be used to precipitate the copper. That would happen until all the copper was used up, and then we'd start to see an increase in pH again until we got to a hydroxide concentration that was suitable to precipitate the magnesium. As the magnesium was then able to soak up the hydroxide would not contribute to a change in pH, and then we'd see another increase as the hydroxide concentration would be added to solution after using up all of the metal ions. So again, kind of a neat way to think about relating that to titrations.